Imagine a mind so far ahead of its time. It glimpsed mathematical truths that wouldn't be formally understood for 2 millennia. A mind that grappled with infinity, wrestled with curves, and devised methods astonishingly similar to those used in modern calculus. This is the story of Archimedes of Syracuse, a legendary figure from ancient Greece, whose audacious intellect took him to the very edge of one of humanity's most profound mathematical discoveries, only to be held back by the limitations of his era. How close did he truly come? And what kept him from unveiling calculus to the world 2,000 years before Newton and Leibniz? Our journey begins in the 3rd century BCE, within the bustling port city of Syracuse on the island of Sicily. This wasn't just any city. It was a vibrant center of the Hellenistic world, a crucible of culture, philosophy, and burgeoning scientific inquiry. Imagine sun-drenched marble buildings, lively markets, and scholars debating profound ideas under the Mediterranean sky. This was the intellectual crucible that forged one of history's greatest minds, a man whose ideas would echo through the ages, long after the fall of empires. Born around 287 BCE, Archimedes was no ordinary scholar. He was a polymath, an inventor, an engineer, and above all, a mathematician of unparalleled genius. Tales of his eccentricities abound, forgetting to eat while absorbed in a problem, drawing diagrams in the sand or on his own oiled skin. His mind was a restless engine, constantly exploring the mechanics of the universe, not just through observation, but through rigorous mathematical proof. He was a legend even in his own time, though his true depth would only be appreciated much later. While often remembered for his eureka moment concerning buoyancy in the king's bath, Archimedes' true legacy lies far beyond practical inventions. His curiosity wasn't limited to solving immediate problems. He delved into the fundamental nature of shapes, volumes, and forces. He laid foundations for hydrostatics and mechanics. Yes, but his most revolutionary work was in theoretical mathematics, where he tackled problems that geometry, as it was then understood, simply couldn't touch. He sought to quantify the unquantifiable. For centuries, Greek mathematicians had mastered the geometry of straight lines and perfect circles. Euclidean geometry provided elegant solutions for triangles, squares, and spheres. But what about the elusive areas and volumes of irregular, curved shapes? How do you find the exact area of a parabola segment or the precise volume of a sphere? These problems baffled even the brightest minds. Archimedes understood that to advance, he needed new tools, a different way of thinking that could bridge the gap between the finite and the infinite. Archimedes' groundbreaking technique was the method of exhaustion. Instead of trying to measure a curved shape directly, he would exhaust its area or volume by inscribing inside it, and circumscribing around it a series of simpler shapes, like triangles or rectangles, whose areas or volumes could be calculated. He would then increase the number of these simpler shapes, making them infinitesimally smaller, until they almost perfectly filled the complex figure. The limits of these approximations would then converge on the exact measurement. Sound familiar? Using his method of exhaustion, Archimedes achieved a truly monumental feat. He determined the exact area of a parabolic segment. He proved that its area is precisely 4/3 the area of a specific inscribed triangle. This wasn't an approximation. It was an exact, rigorous proof. His technique involved summing an infinite geometric series, a concept that wouldn't be fully formalized for centuries. This single achievement is often cited as the closest anyone came to integral calculus before its formal invention. What Archimedes was doing, in essence, was grasping the concept of a limit, a fundamental cornerstone of calculus. He didn't have the algebraic notation or the formal definition, but his intuitive understanding allowed him to approach infinity with remarkable precision. By showing that the area of his inscribed and circumscribed figures could be brought arbitrarily close to the true area, he was laying the conceptual groundwork for how mathematicians would later define derivatives and integrals. He danced on the edge of the infinitesimal, millennia before its time. Archimedes' genius wasn't limited to areas. He also applied his method to the ancient problem of calculating pi symbol. By inscribing and circumscribing polygons with an increasing number of sides, up to 96, around a circle, he was able to narrow down the value of pi with unprecedented accuracy for his era. His famous approximation, that pi lies between 3 and 10^71 and 3 and 1/7, was a testament to his methodical rigor and his ability to push mathematical boundaries through iterative processes. It was a laborious, yet revolutionary, endeavor. If these feats weren't enough, Archimedes even ventured into the realm of truly enormous numbers. In his work, The Sand Reckoner, he estimated the number of grains of sand it would take to fill the entire universe, a universe he conceived of as being vastly larger than his contemporaries. To do this, he had to invent a system of numeration capable of expressing numbers far beyond the Greek myriad, 10,000. This showed his incredible capacity for abstract thought and his fearlessness in confronting truly massive scales, another trait shared with later calculus pioneers. Given his profound insights, why didn't Archimedes fully invent calculus? The answer lies in the limitations of his time. Greek mathematics was largely geometric, lacking the symbolic algebraic notation that would become essential. He had no concept of a function as we understand it, nor a system to manipulate equations with abstract variables. Each problem required a unique, painstaking geometric proof. Without the concise language of algebra, his brilliant methods remained a series of isolated, though incredible, geometric solutions, rather than a unified mathematical system. Tragically, much of Archimedes' most advanced work was lost for centuries. His death during the Roman siege of Syracuse in 212 BC, reportedly by a soldier exasperated by his absorption in a mathematical problem, foreshadowed the decline of Hellenistic science. Many of his treatises survived only through painstaking copying by Byzantine scholars. His groundbreaking method treatise, which explicitly described his mechanical approach to discovery, was only rediscovered in the 20th century, revealing the full extent of his almost calculus. It was a whisper from the past, finally heard. 2,000 years later, Isaac Newton and Gottfried Leibniz, equipped with the algebraic notation, the concept of functions, and centuries of accumulated mathematical thought, independently formalized calculus. Yet, their foundational ideas, dealing with infinitesimals, limits, and the inverse relationship between finding areas and rates of change, echoed the very questions Archimedes had wrestled with. He had built the conceptual bridge, even if the formal road wasn't paved until much later. He was a lone pioneer, charting a course across uncharted mathematical seas. Archimedes' story is more than just a tale of mathematical genius. It's a testament to the indomitable human spirit of inquiry. Faced with profound questions, and without the tools we take for granted today, he pushed the boundaries of human understanding. He didn't just solve problems. He invented new ways to think about problems, methods so powerful they would eventually lead to the very language of modern science and engineering. His work reminds us that true innovation often comes from questioning what is possible. Archimedes of Syracuse, a man born 2 millennia too soon, stands as a towering figure at the dawn of mathematical modernity. He didn't invent calculus, but he came so incredibly close, his intellectual daring laying the conceptual foundations for what would become one of the most powerful intellectual tools in human history. His story is a profound reminder that progress is built on the shoulders of giants, and that even in antiquity, minds capable of grasping the infinite were charting paths for the future, inspiring us to forever push the boundaries of what is known and what is possible.